Hey guys, my name is Prasad. Welcome to my today's video. Today we are going to talk about BFS. So what is BFS? BFS is one of the graph traversal algorithms. There are many algorithms which are used to traverse graph, and BFS is one of them. How BFS works is while traversing from the current node or vertex, all the children from that specific vertex are discovered first, and then each discovered vertex will repeat the same step. Means each discovered vertex, we will traverse to all its children, and then we will keep on going. We will keep repeating the process, the same steps. BFS is very useful when we needed to find the shortest path from the source vertex to all other vertices in the graph. Distance is in terms of number of hops, in the sense number of edges between the source vertex and the destination vertex, and not in terms of the edge weight. BFS can be used in undirected graphs as well as directed graphs to find the shortest path or distance. Because the searching algorithm fans out to all its neighboring vertices, unlike DFS, it does not go deeper and deeper and then track back. It is basically fanning out. That's the reason it is called BFS, that is breadth first search. So in this slide, we will see how BFS works practically. I have taken this example graph, and there are different vertices A, B, C, D, E, F, G, H, and I, and A is the beginning vertex or the start vertex. Here there are three areas. This area is visited. We will keep all the visited vertices in this area. This area is will have all the unvisited or undiscovered vertices. So if the vertices are in this area are not discovered or not known until now, and this area will act as a FIFO data structure, or first in first out, kind of a queue. And you will see I will run a kind of animation here to demonstrate how BFS works. So after starting from A, there are three vertices which are neighbor vertices to A. One is I, F, and B. So first we have taken B, and basically A discovered B. It was undiscovered initially, but now A discovered B, and hence we are creating a tree simultaneously. We can call this tree as a BFS tree. So as and when the vertices will be moving from undiscovered to discovered and from visited from discovered to visited area, we will keep creating this tree. So now B is in discovered area. There is another vertex I, which is a child or a neighboring vertex to A. So A discovered that as well, and the last vertex was F. So as I said, BFS will visit all the neighboring nodes of the current vertex. So we discovered all three of them, and once that is done, we marked A as visited, and we will not come back to A anymore. And as I said, this is a FIFO data structure, this discovered area. So B came first, so B will be moved to visited first. So B came here. Now we will repeat the process. So B has two neighbors E and C. So E is discovered first, and then C is discovered, and now the rest remaining vertex was I. So I is transferred to visited section, but I doesn't have any neighboring vertex. I has A, but A is a parent of I here, right? You can see this relationship. So that's the reason I doesn't have any undiscovered vertex, and hence it will be marked as visited, and nothing really will happen. Now F is the first vertex which came in among all these three vertices. So F is transferred to visited section, and now we will see all the neighboring vertices of F. So if you see in this graph, G is one of them and A, but A is already visited and it is a parent of F. So we don't need that neighbor because it is already visited. So G is the only vertex which is a neighboring vertex, but and it is undiscovered. So G came here. It is just discovered and it is in discovered area right now. And here the tree also demonstrates that F has been F discovered G. Now E was the vertex which was first came in discovered area among E, C and G. Hence E was transferred to visited. And if you see E, there are three vertices which are neighbor to E. One is D, which is already visited. One is C, which is discovered already by B, and another is G, which is also discovered by F. You can refer to this tree. You can by referring to this tree, you will know which node discovered which node. So F discovered G, C was discovered by B, and B is already visited, which was discovered by A. So E doesn't have any undiscovered neighbors. So we are not going to do anything really here. Now it's C's turn to come to this area. Now C is in the visited area, and it's time for us to look for the neighboring vertices of C which are undiscovered yet. And if you see, E is already visited, B is already visited, but D is not. D is still undiscovered. So it's time for D to transfer D to discovered area, and now D is in this area, and we are marking it appropriately in the tree that C has discovered D, and C is now visited. Now among D and G, G is the first vertex which came, which was discovered, right? So it's time for G to go to visited section. But if you see G, all its neighboring vertices are already visited. So for G, there is nothing to do here, and there is only one vertex in discovered area. Now we will move that to visited area. Okay, so D is moved here, and now we have to reach out to all the undiscovered neighbors of D. And if you see here, H is the one, right? It is still undiscovered. You can see it here. So we will transfer that into discovered area, and you see here in the tree, H has been added here as a node, as a child node of D, indicating that D discovered H. Okay, and H is only a vertex in a discovered area right now, so we can safely move that H to visited area. And now our discovered area is empty and the undiscovered area is empty as well. So we are done with BFS. So this is how BFS works. It will, as I said in the first slide, it will basically fan out. So A will explore all its neighbors, and then for every neighbor we will go and fan out and explore all its neighbors. So this process will keep on going. So if you see this tree, this tree can be called as BFS tree, and if you see, it's pretty regular tree structure, and you see all these edges indicating the relations, parent-child relationship between the nodes. But there are more types of edges which will appear in this tree. If you have noticed, all the other edges are red by now because these are the explored paths. But if you see these two edges, these are still black. That means we did not explore, we did not take that path, we did not take that route, right? So these two yellow edges, one is from E to G and another is from E to C. These two routes were not explored when we were running BFS. So these edges indicate that in the graph from the source vertex to the destination vertex, we have more than one path. That means if that is undirected graph, then that graph has cycles. In the sense, there are multiple paths to reach from source to destination. These edges are called as cross edges. Basically, cross edges are the edges which are connecting two vertices which are not directly have the parent-child relationship. So this E and B has a parent-child relationship, and it is denoted by the black edge. But if you see this yellow edge, F is basically parent of G, and E is a child of B, and E and G do not share any direct relationship as such, as a parent-child relationship, but E and G are connected with alternate edge, and hence this edge is called as cross edge. This cross edge is very important when we have a problem to find if the graph has cycles or if the graph is bipartite. So when you have these kind of problems, you can easily solve them with this tree. Let's go to the next slide. So here I will just demonstrate another animation just to show you how BFS works. So this is the source vertex, right? And then when in the first iteration, as I said, all the vertices, all the neighboring vertices of the source vertex are visited, right? And we can call them as one hop neighbors. So you can think of this as a city with some infectious disease broke out in this city, and then after one day, all the neighboring cities got infected, right? And then on the second day, the two hop cities will get infected, and this will happen so on and so forth. As the day goes by, the next hop cities will get infected. So if you see, it is just panning out, it is radiating out, right? So that's the reason any city will from the source vertex will get explored with the shortest path in terms of the edges, and hence BSS is used to find the shortest path. That is the best use case where you can use BSS. I have created a program which is basically you can explore and see how does it work. So basically, whatever was there in the demonstration or the algorithm which I explained until now, the same thing is happening in the program. The complete program link of that particular program is given in the description section of this video. You can just download that video, download that program, and just play around. But here, I just took the core part of that particular program, BSS core logic, and just I'm trying to explain it here so that you will get the grasp. You can basically grasp the logic of that particular program. It is pretty straightforward. So as an input parameter, we will receive the number of nodes in that particular graph and the list of edges. So list of edges we will receive in two-dimensional integer array, and every row will have the start vertex and the end vertex. So that is kind of edge representation. So that's how we will have the total number of edges in this edge list. And then we will build out of this edge list, we will build adjacency map. This is the structure. It is a map of integer and another map, and this map is a map of integer and boolean. So integer is basically I'm storing the neighbors of every node in the graph. So this is the node in the graph, and this map will have all the neighboring vertices of that particular node. So I have a private method in a program which will take care of building up adjacency map. I have not shown it here, but you can just check out the complete program. And then parent array. Parent array is basically used to create the BSS tree. If you remember in the previous slide, I showed it. So for every node, as the assumption here is all the nodes which we are getting are the convenient integers which will start from 0, and the last node number will be n minus 1. If I assume that there are n number of nodes, then the last node's name will be n minus 1. So if there are 5 nodes, then the first node will be 0, second will be 1, 2, 3, and last will be 4. So that's the reason I have taken integer array as a parent to mark. For 0, I will if my start vertex, the start vertex from where I will start traversing the graph. If the start vertex is 0, then the parent will be 0, and then subsequently whenever the neighboring vertices will be discovered, I will mark those vertices with the parent node. And this another array of Boolean values. So I will use this to mark the vertices visited. If they are visited, the value in that particular index will be true. Otherwise, the default it will be initialized with false. And I have created to mimic the FIFO data structure, the discovered area. I took double-ended queue array deck, and this basically will act as FIFO. We will insert from back and we will remove from front. So this will mimic the FIFO data structure or queue. And this is basically a variable which I will be using to handle the case in case if the graph is not graph is having more than one components, more than one connected components. So if you check out the program, I have detailed comments in there. You can just check it and you will understand it, how I am using this component there. And this is how I am initializing the arrays, different arrays. Parent arrays will have the size of number of nodes. Visited array as well will have the same size as of number of nodes. And the parent array, I will initialize all the values with -1. Okay, so now let's talk about the core BFS logic here. So I just separated this core logic from the whole program, and this is actually the heart of the program, which is the actual BFS logic. So the outer loop is looping. It is starting from 0 and it will loop as many times as the number of vertices which we have in the program. And it will start from 0 and it will go to visited array and check if the vertex 0 is visited or not. Or for that matter, any whatever the value of I, it will go and check if that particular vertex is visited or not. If it is visited, then it will skip the whole logic and it will increment I and will go to the next vertex. But if that particular vertex is not visited, then it will go in and we will treat that as a starting point or the start vertex, and hence it is a start vertex. It is its own parent, hence I am setting the parent of I is equal to I, and then we will push it from backward into the discovered array or a discovered queue. In fact, once it is in the discovered queue, we will loop inside the discovered queue until it is empty, until the size of the queue is 0, and we will check this condition outside in the while loop, and then every time when we find it not empty, we will remove the element or the node from the front end. We will insert the element from the back, but we will remove it from the front. So this line, it is removing the element from the front end. And once we get that element or the node, that we will treat as a current node, and then we will iterate over the neighbors of that particular node, and we will be looking for all the neighbors which are unvisited and undiscovered, right? So to make sure it is not visited, we will obviously check the visited array to make sure that it is not visited, and to make sure that it is not discovered, we will check the parent node. If the parent of that particular node is -1, that means it is not discovered until now. Some other node will discover that node, right? And once that node is discovered, we mark that node as a parent of the discovered node. But if the parent node is -1, that means that specific node is not discovered until now. And if that is the case, if both the cases were matched, then we will go inside this if condition. We will add it to the discovered area or the queue from the back, and then we will mark the parent node of that particular neighbor, which is now newly discovered, as a current node. So current node will be the parent of newly discovered neighboring node. Once that is done, for all the neighbors, whichever we will find discovered, whichever we will find undiscovered and undisclosed, we will mark them as discovered, and we will mark the parent of those nodes as appropriately. And then once that is everything is done for all the nodes, the current node we will mark it as visited, because now on we are not going to come back to this current node. It is, if once it is marked visited, it is done. If we encounter this node again, we will ignore it. So that's why we are marking it as visited, and then we are going back. We are going back to the while loop, and here again we will check if the node, if the discovered queue is empty or not. If it has more nodes, we will pick the first from the node, and then for that node again we will repeat the same steps. And now, by now, you are probably able to relate it to what I have shown you a couple of screens back, right? And hope this is making it clear now. So as far as the time complexity of this logic is concerned, time complexity of the BFS, if you see this logic, the outer loop will be iterating n times. So n is number of vertices, as I said. And inside, other steps, all these steps are having all these are constant time execution, right? These are all will get executed in constant time. But this whole for loop, this is iterating. The number of iterations for this for loop will be equal to the degree of the vertices. So the total time complexity of this whole loop is n into the degree of the vertex. So if you have seen the previous videos, and if you consider this as unidirectional graph, then if we sum up the degrees of the vertices, then it will be the number is twice of the age, and that's the reason this whole logic, if we sum it up, it will be equal to this the for loop logic will be equal to the number of ages in the graph. So that is all I have for BFS. So please check out the program, download it, and play with it, and feel free to give me the comments.